Generally, I think what y'all are gonna see is that the grades on these, it looks like we are improving on the quiz grades, which is awesome. Hopefully, whenever you see your quiz grade, um, I tried to give everybody feedback on their quizzes so that if you did lose points, I'm telling you why. Um, on the first couple, I like realized that we had quite a I gave more feedback than others, depending on what, feedback was needed. And so I ended up kind of writing a lot on some people's things. I was planning to go over it. So what I'll do is I'll pass them back and then I'll go through our lesson. And then once I make sure that I've gotten through everything I needed to get through today so that we're good to do our homework, then I was going to talk about those quiz answers. Um, so I'll make my slides for today, and then we can start passing back those quizzes. Let's see. So when I call your name, if you wouldn't mind coming up and grabbing yours, Jesus, John Deltz, Joshua, McMahon, Burke, Joshua Reed, Roman, Tyler Lennox, Elizabeth, Axel, Abube, Jay Ruckle, Carson, Sahil, Jake, Thomas, Cassandra, Raya. And if I'm mispronouncing your name, feel free to correct me. And sorry if I do. Raul, Mariam, Anne. And that looks like everyone else is here. Okay. So that was the first one, and I'll try to get you back your quizzes more frequently, but I was trying to get caught up with making sure we had everything ready for this week. Raya again. Cassandra's not here. Elizabeth's not here. Axel. And Daniel. Bert. Tyler. Uh, Roman. Joshua Reed. Carson. Thomas. Jesus. Raul. John Deltz. Joshua McMahon. Sahil. Colby. No, Colby. Connor. Elizabeth, I have some quizzes for you. And Marianne. Here is quiz 2, and then I have quiz 3. Thank you. So if you didn't get a quiz, it's maybe because I have them here. If you didn't hear your name, let me know. Otherwise, yeah, so I tried to give feedback on those quizzes. If you see something that you are unsure about a quiz answer, always let me know. If you have questions about anything, getting those addressed sooner rather than later is always good because what you'll see in classes is that stuff kind of builds up on itself. And then this is even more true in the summer because things go so fast. So it's like if we miss something, ideally we want to get that sorted out as soon as we can so that if we make any mistakes, we're understanding them, we're learning from them, we're fixing them, and then hopefully that means that we don't make those mistakes in the future. Homework is a really big important part of that too, because the homework is where you're getting most of the practice for like everything that we do in the class. So if you haven't done homeworks 1 and 2 yet, um, I would very highly recommend that you get started and turn those in like as soon as you can, because after this week we'll be 3 homeworks in and we'll basically be like almost a third through the class, right? Because it's a 10-week class. This is the end of the 3rd week. So we're like almost halfway done already. After the first exam, if you are like in a bad spot, you can still recover after the first exam, but it becomes harder and harder to recover the longer that we kind of like wait on doing the things that we need to do. So yeah, Friday help sessions are a really good opportunity because the way that I would recommend that we're going through the class is you come into class on Tuesday, we do all the things we're supposed to do as students when we're in class. When you leave here on Tuesday, you're going to be prepared to do about half of the homework, plus or minus. So like ideally, you are doing about half of the homework Tuesday, Wednesday. We're coming into class on Thursday. You're learning about what you need to do for the second half of the homework. Then Thursday, Friday, we're finishing up the homework. Friday is the help session, right? So I take time out of my day, hour and a half downstairs, open office hours, kind of like tutoring slash it's your time so that if you need help, if you need one-on-one help, if you're struggling to understand a concept, any of that stuff, it's your time, but that time is going to be more useful if we've already done some of the legwork in advance, right? Like if we're showing up completely unprepared, that's better than not showing up at all. But if we can show up and having maybe attempted some of the homework problems, then we're going to be able to ask better questions. We're going to be able to get more out of those help sessions. So if we are in a spot where there's things that are preventing us from completing the assignments, let me know. Let's try to work those things out so that we can be making progress and not just like stagnating. So that's my long-winded explanation. Hope that all makes sense. Let me know if there's questions or concerns about anything. Oh yeah, so today we are going to be talking about multi-group diffusion theory. This is very much just like a continuation and kind of evolution of what we did last class. And this is going to be the end of the scope of our exam 1 material. So last time we started to talk about energy dependence and why we need to care about how neutrons are distributed in terms of energy in a reactor. Cross sections, all of those microscopic and therefore the macroscopic cross sections, they depend on the energy of the neutron. So if neutrons have lower energy, it's more likely that they can cause like U-235 to fission. So cross sections depend on the neutron energy. The reaction rates depend on the cross sections, so therefore the reaction rates are also energy dependent. Um, yeah, most like in our reactors, when we use U-235 or plutonium-239, these are fissile nuclides, which means they will fission, but they like to have a low energy neutron make them fission. It increases the probability that that absorption results in a fission event. So we need to slow our neutrons down in like the thermal reactors that we use in the United States. When neutrons come out of fission, there's the chi of E, which is the fission spectrum, and that tells you the probability per unit energy that a neutron is born with a specific energy. So if you look at that plot, the peak of that plot is at 1 MeV, so that like most likely energy of a neutron to come out of fission is 1 MeV, which is pretty fast compared to the thermal energies of like 0.025 EV. So neutrons come out really fast, and we need to slow them down to increase the likelihood that they cause a new fission. The way that we slow them down is that's the term moderation. When we say we have a neutron moderator, it's a material that causes neutrons to scatter, losing energy becoming thermalized and allowing them to cause a new fission event. So we make our neutrons scatter, they lose energy, they're more likely to fission. So last time that we were here, we took our neutron diffusion equation and then we set it up for two separate energy groups. So what that looked like was we were assuming that instead of having like energy as a continuous variable, we discretized what was happening such that we had one group where we could characterize everything in terms of the properties of that group, and we used two groups. One was the fast group, one was the thermal group. Neutrons are born fast, so E0 here corresponds to like the maximum energy of the fast group. And as neutrons exist in the reactor, they lose energy. So that's why this E0 is like energy is going positive. Increasing energy is to the right, but the indexing goes backwards because that's the neutron life cycle. They start fast on the high end of the energy scale, and then as they scatter, they come this way on the energy scale, hopefully getting thermalized and then causing a new fission. Question?
So neutrons come out, like kind of start at the high end of the fast group.
Yes, absolutely. And like they are, if you look at that fission spectrum, some of them will be born in the thermal group, but like 95% or more are going to be born fast. So yeah, very much it's like they're almost all born in this group, and then they need to make their way into the thermal group so that they can cause new fissions.
So are they born like somewhere in the middle of the spectrum, or are they born at the far end of the respective spectrum, like are the 5% at one at E1?
So I was trying to find the slide that answers that. The thing that answers that is the fission spectrum. So that's a great question, and I'm going to go to Google Classroom real quick to pull up the plot for that. That was from our slides last time. We saw that plot of the fission spectrum, which is that chi of E. My computer's going really slow. Oh, it's because my pen, sorry. So it's a really good question. It, it's it's a thing about these neutrons where we basically have like a probability density that tells us the likelihood of finding these fissioned neutrons at a certain energy. So I'm just going to try to find that real quick. I think it's right here, not this one, this one. So these two plots, the red one here, that is the fission spectrum. So this is a probability density function, and this is on a this is like linear scale, which kind of makes it hard to see. But if you go to this plot, then this is chi of E, but on a log scale for energy. So this makes it a lot easier to see what's happening as the energy changes. Notice that so at 1 MeV, that's the peak of our distribution. So that's where the probability of a neutron coming out at that energy is highest. And then this average is kind of, it's effectively right. This distribution is effectively right skewed, which means that, and it's easier to see that it's right skewed if you look at this plot, that if the most probable energy is 1 MeV, the average energy is like 2 MeV. It's a little bit to the right of 1, because if this is my peak, my average is going to be corresponding to somewhere over here. But yeah, so as we get lower energies, the probability of a neutron being born at that energy becomes lower. So in principle, what you could do is if you have this function and this thing right here, this is like, and it's kind of grainy, but if you were to look at the actual slides, you can see what this function is. That's a way that you can analytically determine what this distribution is. And then if I wanted to predict what the fraction of energies are coming out of a certain interval is, what would I do with this expression? Like if I had this expression and I want to say how many neutrons are coming out with an energy between 0 and 5 eV, integrate that function over that interval, right? Because this is a probability density function, and if I integrate it over some interval, it tells me the probability of finding my neutrons in that interval. So yeah, that's what we would, that's how we could figure out exactly what fraction we're coming out of which energies. So yeah, so we had two energy groups. Within each group, we used constant material properties, and then we said that the total flux can be thought of as having one part that's in the fast group and one part that's in the thermal group. And if we were to add those fluxes together, that gives us the total flux. Um, in terms of that fission spectrum, if you have like a continuous distribution, you want to be able to say this is the probability of finding the neutron of the neutrons coming out in some range. But if we only have two groups, we don't need a distribution, and we can just assign a fraction that are born into group one and a fraction that are born into group two. And whatever those fractions are, they have to add up to 100%. So like in our example, chi1 for the fast group is probably like 99% or like 0.99, and then chi2 is like 0.1% or something like that. Uh, so yeah, and then we also just defined an average group speed V1 and V2 for the neutrons in each group. And then what we did is we said, we looked at this picture, which is showing what kinds of production mechanisms we have, what kind of loss mechanisms we have, and um, and so we have production, which is a fission production, which is a gain. We have neutron absorption, which is a loss. We have net leakage out of each group, which is also probably a loss. And then we have scattering between each group. So the scattering can either be positive or negative, depending on if the neutrons are scattering out of the group. That would be a loss for that group. But the neutrons from the other group can scatter into our group. So that would be a gain for that group. And the gain for one group is a loss for another, because if I have the neutrons scattering out of this group, they're ending up here. And if I have neutrons scattering out of this group, they're ending up there. So those groups are coupled because of the scattering, kicking neutrons from one energy to another. They're also coupled from fission because we can have fission neutrons born into each group, and we can have fissions caused by neutrons that were initially in either group. So when you do conservation, rate of change equals rates of gains minus rates of losses, and you work out what are the terms for the production and the losses, this is what we get. And this is what we get for group one and group two. And these equations look very similar because they had similar production and losses. We just basically have different subscripts to tell us which groups are participating in those reactions. So like in this first equation, this is the fission production of neutrons that are being born into group one. And this term represents the fission density, the fission rate density from group one neutrons. This represents the fission rate density from group two neutrons. And this says this is the fraction of all of those that get born into the first group. So this is like the total production for group one. This is scattering from group two into group one. So this is a gain term in the group one equation because neutrons are scattering into group one from group two. And then this is the outscattering term for group one. This is scattering from group one into group two. So this is a minus sign for group one because they're leaving one and going into two. And if you look in the second equation, these terms are equal and opposite because whatever is a loss from group one into group two is a gain into group two from group one, and opposite for this term. So this is just a conservation equation. This just says this is my rate of change. Anything with a plus sign over here is a gain. Anything with a minus sign is a loss. And this is the net leakage, which is kind of a funny term because the net leakage can either be positive or negative depending on the context. Like if your net leakage is positive, it means neutrons are leaving and it's a loss. But it's possible that your net leakage is negative, in which case it actually means neutrons are going in. So the leakage term is kind of funny, but generally if you call it a loss, you're fine on that. So these are coupled differential equations because the solutions are phi1 and phi2, and we have a phi1 and phi2 in each equation. So this is just kind of like a review of what we did last time, and we talked about how we could write those equations in steady state. If it's steady state, then the d by dt term goes away. And then this is just saying gain rates equals loss rates because the rate of change term is now dropped out. And then we don't have to write time arguments anymore because it's a steady state problem. But here we are adding position arguments on our cross sections just to acknowledge that the materials could be changing as a function of position. And this is the net leakage term, but if the material properties change with position, then this diffusion coefficient can't come out of this operator. Whenever on the previous slide, when we have this d Laplacian of phi, we can pull the d out if it is not if material properties are constant or if there's no r dependence. But if we have r dependence, then d cannot come out of this operator. So that's what the net leakage looks like. It's just that we can't remove the diffusion coefficient if it's not constant with position. So that's all I've done with that net leakage term is rewritten it without pulling d out. And so that's just this is review of last time. And the last thing that we did was we said, okay, if this is my steady state equation, we can look at it like a k eigenvalue problem, and then we can recast the equations as a eigenvalue equation. Where we have our loss operator equals 1 over k times our production operator. And in this case, the production operator is the fission production term. So that's where the 1 over k gets multiplied. So these are the same equations as 4.122 and 4.123 in Svetkov's notes, just to make sure that we are, just so that we can kind of see the connection between what I'm talking about in class and where you could find this stuff in the notes. So talking a little bit more about energy dependence, because what we're going to do next is actually start treating E as more like a variable instead of discretizing it. So in terms of talking about the energy distribution, the flux has energy distribution as well. And if our flux depends on energy, we don't call it the total scalar flux. We call it something else. Do y'all remember what we call it when the flux has energy dependence? All we do is we add the word energy dependent in front. So it's the energy dependent scalar flux. So phi, if you see phi with an E inside of it, it is an energy dependent scalar flux. So when we talk about scalar flux without the energy dependent part, it's a path length rate made by all neutrons with all energies moving in all directions. And it's that total path length per unit volume and per unit time. If you have energy dependent scalar flux, then you're acknowledging that these neutrons actually have a distribution in terms of energy. So the units of this term look just like the regular scalar flux, that we have a path length, a neutron path length per unit volume, per unit time, per unit time. But if it's energy dependent, it's also per unit EV, per unit energy of the neutrons in my uh, per unit energy of my neutrons. So the way to interpret the energy dependent flux is that it's a path length rate density, but it's a density in the volume and it's a density in terms of energy. So same units, it just picks up per EV if it's energy dependent. So this has the same physical meaning as the regular flux. It's just that the neutron has a specific energy. So it's path length of neutrons per unit volume, per unit time with some specific energy. And we had already talked about these other two things, but I wanted to review energy dependent flux. Chi is our fission spectrum. That's that probability density function that you can integrate to say what fraction of your neutrons are coming out of a certain energy. The similar thing for scattering was the macroscopic differential scattering cross-section. This is like a scattering cross-section times a probability density function that ultimately tells you the scattering cross-section to go from some initial energy EI to some final energy EF. So the neutron comes in, it's got some starting energy, it hits something and scatters, it has a new energy after the scattering event, and this gives you a cross-section, same cross-section units, reactions per unit distance traveled, but it's telling you the reactions per unit distance traveled that result in a neutron being kicked from energy EI to energy EF in a scattering event. So yeah, mostly whenever with the energy dependent flux and the scalar flux, if you see that energy argument, or if you see per EV units in the units, then you know it's an energy dependent quantity. So I recognize that that can be confusing, but that's just that's something that we have to be able to recognize from the context. So if you look at how we were talking about neutrons having a distribution in energy, and this is what that flux per unit energy would look like. This is technically flux per unit lethargy, and you don't have to know if you've taken 304 before, you might know what lethargy is. We're going to talk more about that in detail. For now, I want you to know this plot is basically just like flux per unit energy. We're just rewriting it as this new thing called lethargy. But in terms of physically how to think about it and what it's showing, you can think of it as telling you basically the same thing as the energy dependent scalar flux. So what this is showing is saying this is the shape of my scalar flux distribution as a function of energy. So we were talking about how neutrons are mostly born fast at like 1 MeV. So that's 1 MeV on my axis. And notice that the peak of this part of my distribution, that's going to correspond to the peak of like my fast neutrons being produced. So my neutron production looks like, the distribution looks like the fission spectrum. It looks like chi of E. So at the fast energy range, this distribution just pretty much looks like chi of E. It just looks like the fission spectrum. So at high energies, the energy dependent scalar flux just looks like the fission spectrum. It looks like that chi of E function. That's what we're talking about right here. In this, in this energy range from say um, around 10 to the 5 EV to like 10 or 20 MeV. So that would be like my fast range. Neutrons are born fast, they hit my moderator, which makes them slow down. So what you're seeing in this intermediate range is the slowing down process. You're seeing fast neutrons scattering, losing energy, and coming down this little part of the graph. The shape of this graph looks like 1 over E. So as neutrons slow down, they follow, oops, I can't spell. They follow 1 over E. So if I were to ever ask you, what do neutrons draw an energy distribution of neutrons? This is the plot I want you to be able to show me. And when I ask you to show me this plot, I want you to be able to tell me important things about the distribution. I want you to tell me, what does the fast spectrum look like? It looks like the fission spectrum. I want you to tell me, what do the intermediate energies look like? It looks like 1 over E. And I want you to tell me what the thermal energies look like. And so as these neutrons get slowed down, what eventually happens is that the neutrons effectively will come to thermal equilibrium with the moderator that they are scattering it. So you almost want to imagine these neutrons just kind of like aimlessly bouncing around. Every time they scatter in the moderator, they're losing a little bit of energy. And at the point that they become thermal neutrons, in homework 1, we calculated the thermal neutron energy using like that E equals 3/2 kT equation. And we showed that if the temperature was room temperature, like around, if it was around room temperature, those neutrons have an energy about 0.025 eV. That is the thermal neutron energy, and it's the energy that they will have when they come to thermal equilibrium with the moderator atoms that they're surrounding. Just like if I were to leave a can of, if I take a cold can of Coke and I put it in this room and I leave it for a while, eventually that cold can of Coke is going to come to thermal equilibrium with the atoms in this room, and it will be at the same temperature as the atoms in this room. The neutrons basically do the same thing, right? They're born in the fast spectrum. They're born very fast with a lot of energy, but as they scatter, they lose energy. Eventually, they become thermalized when they are in thermal equilibrium with their environment. And we talked about early on that if the neutrons are vibrating isotropically, then we can characterize their distribution just with their temperature. And we said that that distribution looks like a Maxwellian distribution. So in my energy dependent scalar flux, what the neutrons look like in the thermal region is just that Maxwellian distribution. In the thermal region, they follow a Maxwellian distribution. And that's the M of E. Maxwellian distribution is a very common distribution. You can look it up, but it basically is kind of like it looks like this. It looks kind of like a normal distribution where it's peaked at the like average energy of our molecules in our medium. So if the peak of this Maxwellian, if this energy right here corresponds to the peak of my Maxwellian, we're saying that that is like the thermal energy. That's like the, E equals 3/2 kT. That's like corresponding to the average temperature of our medium. What do y'all think is going to happen to this distribution if we heat the reactor up? If, like, say this plot is at 300 Kelvin and we heat the reactor up to, say, 500 Kelvin. How do we think that's going to change the distribution if we were to heat the reactor up? Sorry? It's going to shift, it's going to shift one part of the spectrum to the right. And if we heat the reactor up, is it going to affect the fission spectrum? Is it going to affect the nuclear physics? Is it going to affect the Q value of that reaction? No, right? The fission spectrum is it's governed by nuclear physics, it's governed by Q values, and that doesn't really change if you change the temperature. The slowing down process also, this slowing down process is still happening at pretty high energies. These energies are so much higher than like the thermal equilibrium energy that what happens in terms of temperature doesn't really affect those energies. Those neutrons are basically just their energy is their kinetic energy, which is much bigger than like the vibrational energy in the medium. So the only part of our spectrum that is changed from a temperature change is the Maxwellian, and it'll either shift to the right or the left, depending on if we heat the material up, then it's going to push that average to the right because your temperature goes up, therefore your average energy goes up, or that shift spectrum could shift to the left. The Maxwellian spectrum could shift to the left if you were to cool the reactor down. Right. So we're saying just this little part could shift to the right or it could shift to the left, which would shift this spectrum. Like in the example that I just gave, it might cause it to shift something like that to the right, or it might cause it to shift to the left if you have things cooling down. So hopefully that makes sense. And this is for now, this is the picture that we want to have for like what does the neutron energy distribution look like. Fast part looks like the fission spectrum, slowing down looks like 1 over E, thermal part looks like a Maxwellian distribution. So that Maxwellian distribution, like we were saying, it occurs because neutrons are coming to thermal equilibrium with the moderator. So that's the picture to have in our brains for like, what are these neutrons doing? It's kind of just like they're like atoms in this room. They're just bouncing around, slowing down, eventually coming to thermal equilibrium. And at that point, their energy is low. They're very likely to cause a new fission and make new fast neutrons. And from that homework 1, we had calculated what this thermal energy is, and we said it was about 0.025 eV. At least that's what you should have got on homework 1. So if we're thermal, if we're in this thermal energy range over here, from here to here, the neutron energy is so low that it's possible that that neutron can hit like a nucleus and gain energy in that collision. So in the thermal range, we actually have upscattering can occur. Neutrons can upscatter. So we'll just say upscattering is possible. It's supposed to be scattering. Upscattering, for a neutron to gain energy in a collision, if a neutron collides with another particle, what has to be true about that other particle if the neutron gains energy in the collision? Perfect, right? If you think about energy conservation, if the neutron hits something, for the neutron to end up with more energy than it started with in that collision, the thing it's colliding with has to be more energetic than the neutron was. So at low energies, that's possible because the neutron energy is relatively low. But once you're in like the intermediate or the fast range, the neutron energy is much greater than the vibrational energy of any of the atoms in the lattice. So you basically don't really have much upscattering in the thermal range or the fast range. In the fast range, you're basically slowing down to the intermediate range. And in the intermediate range, you're mostly downscattering into the thermal range. When you're in thermal, it's possible that you could upscatter into the intermediate, but the opposite doesn't really hold. Um, in this 1 over E range, so this is showing two plots. It's showing the fission spectrum in green, but it's also showing the microscopic fission cross-section in black. And notice that in the intermediate regions, in the slowing down region, that's where sigma F has all these crazy resonances. So in the slowing down region, it follows 1 over E, but we can see some deviations like spikes down or spikes up, and that's because of the resonances in the microscopic cross section. So these deviations occur due to resonances. In our microscopic cross section. And oh yeah, and then we're also giving a range of these energy groups. So we're saying thermal goes from basically 0 EV to about 1 EV. We're saying the slowing down region is from about 1 EV to about 100 keV or 10 to the 5 EV. And then we're saying anything bigger than 10, so this right here is 10 to the 5. And then anything bigger than 10 to the 5, we're going to consider fast. And oh yeah, so this is a good picture to have both to just see what the energy dependent flux is doing, as well as how the fission cross section relates to that. And then if you were to start thinking about like not doing 1 or 2 energy groups, but actually doing a whole lot of energy groups, like maybe 100 or 1,000 energy groups, that's kind of like showing down here how you could think about that. That like this little interval right here is going to correspond to this little interval right here. And so we could, instead of having very big energy groups, we can make those groups smaller and smaller and smaller, almost like we're doing like we're going from like discretized, like we have a bunch of points, to having like a continuous function. And that's what this picture is going to help us get into. Whoops. I'm gonna make sure. Okay, I think I just forgot to take this blank off. Oh, I'm not going to fix it. I'll just leave it since you can probably already see it on your side too. Or I guess on your slides, is it on the ones I provided, is that a blank or is that missing? Or is that there, or is this equation right here in red? Okay, sorry about that. That was just my bad. So this equation up here is our group 1 equation that we've been talking about. And going from that k eigenvalue equation for like one group to this equation, which is an energy dependent equation, notice that the diffusion term doesn't really change. The net leakage term, all we're doing is replacing the diffusion coefficient and the flux with energy dependent quantities. So we're going from discretizing over the energy group to talking about everything being as a function of energy. This sigma S plus this sigma A, that's kind of like giving us a sigma T. And then this term, which is representing scattering into, this is for group 1. So we're scattering into group 1 coming from group 2. Therefore, this is like a gain term. And we write this as this in scattering integral. So instead of using a fraction to talk about the probability that scatter from group 2 into group 1, we're using the differential scattering cross section, which gives us like a probability density of being scattered from one energy to another. So this is the corresponding term here, but just with energy dependent quantities, going from a fraction to going to an integral definition of those probability density functions. And then doing a similar thing with the fission term, where instead of going from a fraction, we're actually just using the fission spectrum. And then instead of talking about the net production rate in group 1 and the net production rate in group 2, we're using an integral to say this is the net rate of neutrons being produced over the entire energy range. So in these equations, there's an E and there's an E prime, and I want to make sure we're clear on which is which. E prime is the initial energy, and E represents the final energy. E is like the variable that we're tracking, and E prime is some initial energy of neutrons. So this is basically saying I have neutrons that are in some other energy E prime. They're having a scattering event that's kicking them into my current energy E, which is the energy group that I'm keeping track of. And this is similar. This is saying I have fission neutrons being produced at all energy ranges, but then I'm only considering the fraction of those that get born into my specific group E. And so scattering and neutron starts at one energy. It has a reaction that kicks it to a new energy. That's why you have different energy values here, because you start at a different energy than you end up with when you have a scattering reaction. At least you can change energy in that reaction. And similar thing with those fissions, right? It's an incident neutron that causes a fission. Those fission neutrons get born at a new energy. So E prime is the energy of the neutron that is causing the fission. E is the energy of the neutrons that are coming out of that fission. Hopefully that makes sense. So this is just explaining more about what those terms say in words. Just like with the regular diffusion equation, I want y'all to be able to look at an equation like this and not get scared. I want us to be able to think about the units of every term, physically what each term is representing. And if we can do that, the symbols become a little bit less mysterious. And like the first thing to recognize is that this equation, it might look complicated, but all it says is rates of change equals rates of losses. And in this case, every term has units that look like, so if you have an equation, every term, and when I say every term, I mean like every collection of things grouped together. So this one, that's what I'm calling term 1. This is term 2. This would be term, and I color coded it for you too. That's term 3, and then this is term 4. So if we have terms, every single one of these terms has to have the same overall units because it's an equal sign, right? And it means the units on the left have to match the units on the right. So if I can figure out the units of any of these terms, I know that all of the other terms have to have the same units. So like if I think about term 2, I've got a sigma t times a phi. And so what are the units of total cross section? Perfect, 1/centimeters. And then what are the units of a scalar flux? Perfect. So it's neutrons per centimeter squared per second. And this is technically energy dependent scalar flux. So it just also picks up the extra per EV units, right? So this would also be per unit EV. So notice if I multiply these units together, then I have neutrons in the top. Every term is going to have these same units. I'm going to have neutrons on the top. In the bottom, I've got centimeters times centimeters squared. So I've got centimeters cubed. And then I've got seconds, and I've got electron volts. So that term too has those units. And if you work out the units of every other term, overall, they have units of neutrons per unit volume, per unit time, per unit energy. So thinking about those units, the way that we would express that in words is that this is a rate density per unit energy. It's a rate because it has per unit time. It's a density because it's per unit volume, but it's also per unit energy because it's an energy dependent quantity. So you could think of these as energy dependent reaction rate densities. It's a reaction rate density per unit energy. And if you worked out the units on all of the other terms, they should have the same units. Some of these other terms are a little bit more complicated, but we can do the same kind of deal. Let's think about this scattering term. We already said what the units on the energy dependent flux are, right? That's going to be neutrons per unit. You could write it as per unit area per unit time. Notice that this is one definition. I could have also said that this is a neutron path length per unit volume, per unit time, per unit energy, and everything would have worked out the same way. So that's the units of phi. The units of my differential scattering cross section. How about the units of my differential scattering cross section? What units does it have? It has more than just 1/centimeters because this differential scattering cross section, it's like a sigma s times a probability density in energy. So it has the same units as sigma s, but it also attaches the units of a probability density per unit energy. So the probability density per unit energy has units of inverse energy. So that means that this differential scattering cross section has units of inverse distance, inverse energy. And and I forgot my units here because I'm being lazy. But remember, this is also per unit second per unit energy, energy dependent flux, differential scattering cross section, and DE has units. That's a differential of my energy. So DE also has units of EV, or whatever my energy units are. And so notice, if I multiply all of these units together, don't I also get neutrons per unit volume, per unit time, per unit energy? Because these EVs right here can cancel those EVs right here, but I've still got EVs left over on my energy dependent flux. This is an exercise that we kind of have to be able to do this, right? Because if you can't do this for every term in the equation, when you get an answer, how do you know that the answer has the right units if you don't know what are the units of the things that were originally going into it, right? So I harp away on this because it's like critically important. So we're seeing this, we're practicing it. If there's any question, so if we think about those units, we know generally what each of these terms kind of represents, right? Whenever we see the sigma s, we know that that's telling us something about scattering. When we see a sigma f and a nu f, we know that that's telling us something about fission. When we see this term, we know it's telling us something about leakage or maybe diffusion. So like we have bits and pieces, and I just want us to be more sophisticated with our expressing these quantities so that we're being more detailed, we're being more precise, and our definitions agree with the units of every term. So if you think of this first term as a net leakage rate density per unit energy, then it tells you what the quantity represents, but it also has qualifiers that explain that's what the units of my term are telling me. And that can just help make sense of the overall equation is balancing these reaction rate densities per unit energy. Um, so yeah. And then I also just wanted to make sure that we were defined specifically like for the in scattering term and for the fission term, how we could define that understanding all of these E primes and these E's. So yeah, if that's the energy dependent diffusion equation, and this is the understanding that we want to have about all these terms. And my feeling is that once we have this understanding, the equation is less scary because we realize this is just a kind of complicated looking conservation statement that's just saying production rate density per unit energy equals loss rate density per unit energy. So we've got this equation. It's a function of energy, but that equation, we are not really going to be able to solve it. We're kind of out of luck if we really want to solve that equation, because ultimately what we're going to be solving for is phi, which is a function of position and energy. The solution to that equation is an energy-dependent flux. So it's going to be some complicated function that's a function both of space and of energy. And so we've seen how to deal with a partial differential equation before where the variable we were solving for depended on multiple things. And how did, like when we had time dependent flux and it was a function of position and time, how did we deal with that in our differential equation?
Variation of variance.
Perfect. Yeah, we separated it. In that case, we separated it in space and time. Here, we can separate. So we have this energy dependent flux, this phi of R and E, and we're saying, let's see if we can also separate this. Let's see if we can separate him into a space function, R of R, and then this energy function, which we call phi, capital Phi of big E. So R of R, same kind of interpretation as the way that we thought about it when it was one group diffusion. That's like our spatial space function, spatial shape function, sorry. And the solution of that is going to look like that same Helmholtz eigenvalue problem. It's going to basically be those same kinds of flux shapes that you saw for those geometries like a sphere and a cube and all of that sort of. Um, Here, there is a thing that is different in that we have to decide how we normalize this function. And typically, the way that that's done is such that the shape function is the whole thing is normalized so that the shape function gives you your total scalar flux. Um, so essentially, what we're saying is that if I have energy dependent scalar flux, if I have my energy dependent scalar flux, and I want to get the total scalar flux, all I'm going to do is integrate the energy dependent flux over all energies. And then this will tell me about the path length rate per unit volume of neutrons of all energies in all directions, because I'm integrating the energy dependent over all neutron energies. But what we're saying is that we can rewrite the energy dependent flux as this R function and this phi of E function. Hopefully that's okay. I'm just replacing phi of R and E with the separated form. And now I have a shape function times an energy function integrated over energy. So how can I simplify that? What can get pulled out of that integral? Absolutely, right? The shape function only depends on space. Therefore, if we're integrating it with respect to energy, it's a constant and it can just get pulled out front. So I'm going to have an R of R times an integral of 0 to infinity of just the energy part of my function, big phi of E dE. And that's a multiplication. So if I want to normalize this such that the scalar flux is the shape function, then what do we have to normalize this energy dependent flux to so that my phi of R is equal to my shape function? In other words, what is this energy integral, big phi of E dE, integrated all over all energies? What does that have to equal for my phi of R to be equal to the shape function? Sorry, say again. Um, we want, so I guess just to make sure I'm expressing what I'm asking clearly, we're trying to make this equal just this. But right now, it's being multiplied by this integral. It has to be normalized to one, right? If that whole thing is normalized to one, if I integrate this over all energies and it gives me one, then by definition, this phi of R will equal the shape function, right? If this is normalized to one, then that condition that we wanted to have is met, that the shape function gives me my total scalar flux. And because of the original equation being homogeneous, whatever constant we throw up front is going to always be a solution to our equation. So the C that comes up front is kind of arbitrary, and we just kind of throw it in at the end. So ultimately, this energy dependent flux, it's going to look like a flux magnitude times a shape function and times that energy function, where that energy function is just normalized to one. Questions about this or just the bad sounds outside? Oh, yeah.
Is it okay to use that like CFI for pretty much everything? Because I see that it's in the notes that minus.
Yeah, I mean that's a
Like
good
the power magnitude.
yeah, the CFE is like it's the flux magnitude, and usually you will find it from the reactor power. At least you can actually find it in lots of ways. If you look at homework 2, I gave you a problem where you're finding it from the fission rate. But yeah, if you know something about the reactor, that's where CFE can come from. In the notes, it always comes from reactor power. And if I just to real quick pull back to the table that we've seen before, because it's a good thing to mention. And I think it's on these notes. Yeah, perfect, right? So that these in this table, all of these C fees are coming from the definition of reactor power, and then it's like if you know the power and you know everything else, then you just carry out the integration of your power function because the power is like an integral. You carry out on the integration and you get C fee by itself, and that's where these terms come from. But yeah, that's generally where we'll start is just with that equation. If we know our geometry, we'll know our shape function, and then we can work out what the C is from some other information like the reactor power or a fission rate or a leakage rate or something like that. Good question, thank you. So this is showing how we could do this using the reactor power. So these are the definitions of reactor power that we've seen before. The only reason that it's more complicated is that our flux depends on energy. So as well as integrating over the volume, we have to also integrate over energy as well. The kind of the way to think about that is if you have a power density and you want power, you take the power density and you integrate over the volume. That's what we did before. And now this expression right here, this is like a power density in energy. And so if we're to, let's just think about the units of this. What's the units of EF? EV per what? Per fission. If we want to be precise, it's EV per fission. And then if we also want to be precise about sigma F, it's the number of fissions per distance traveled, per neutron distance traveled. And then we had already said that the phi of R and E is it's like a 1 over volume times time times EV. Right? So the fissions, which is kind of like a fake unit, like we didn't have to have the fissions in there, just like we didn't have to have the neutrons in there. It's kind of a fake unit. The fissions cancel. Oh, but I am bad with my definitions because if I put a centimeters cube down here, then I actually need a centimeters up top. It's either a path length rate per unit volume, time, and energy, or you just call it 1 over centimeters squared. But so I forgot my centimeters up here. But now the centimeters up top cancels the centimeters on the bottom, and then the EVs up top will cancel the EVs on bottom. Um, and um, But this DE has EV units. And then DV has centimeters cubed units. So like when the dust settles and I cancel out everything that I can cancel, what am I left with but just EV on the top and seconds on the bottom? And EV is a unit of energy. So if I have EV per unit time, that is a power. I would probably just have to have a conversion factor to go from EV to like joules. But so the units make sense. And effectively what we're doing is we're taking a energy dependent density, we're integrating over volume to knock out the density part, and we're integrating over energy to knock out the energy part. So that's just explaining the units, and this is just the same power density expression we've seen before. You're just throwing in an integral over energy as well. And so if this is ultimately what we have to integrate, then we can simplify this a little bit because like all of these are constants. So these can all come up front. So I'll have an EF, I'll have a sigma F, I'll have my C phi up front. This shape function depends on position, so it can go inside my volume integral. So I'll have the integral over my volume of my shape function, dv. And then what's left is my phi of E being integrated over energy. So I'll also have 0 to infinity of my phi of E dE. And we've already normalized this to 1, so that's actually just going to simplify out of our equation. And what you're going to end up with is that P fission is EF sigma F C phi times the integral of our shape function dV. Because if we've normalized this to 1, then that's what this simplifies to. So if you're gonna get the power, you basically take your energy dependent scalar flux, you integrate over volume, you integrate over energy, and you include the multipliers, your EF and your sigma F, to give you units of power. So the normalizing here, the figuring out what that constant is going to be is a little bit more complicated in terms of like you basically have different ways that you can pick out what the constant looks like. And ultimately, as long as you have unit consistency, it doesn't matter how you do it. Generally, the constants are chosen such that your shape function keeps shape function and flux units. And then we can kind of assign whatever arbitrary units we need to phi of E to make the units work out. That's why on the previous plot, where it showed flux per unit at lethargy in arbitrary units, that's a consequence of the fact that however we normalize that energy part, it's kind of arbitrary. So if the reactor is a real reactor, we're kind of out of luck trying to analytically solve the energy dependent diffusion equation. But what we could do instead is just take that diffusion equation and integrate over a small range, and then use what happens in that range to correspond to average properties for that like small group. And then so if we want to do that, then we can take our whole energy spectrum and break it up into a bunch of little groups. And each of those groups is going to have a certain range. So we're going to break the range into capital G groups. So G is the total number of groups. Like if I had a 100 group model, then big G would be 100. And if I set up G numbers of groups, each group has its own interval. And the way that we define this is that the energy interval of a group, it's always going to be between E sub little g and E sub little g minus 1. This is always going to define the energy of group little g. Like if little g is 1, if I'm in group little g equals 1, then I'm right here. And notice my right bound, my high bound is E0, and my low bound is E1. And doesn't that agree with this definition right here? Isn't this G minus 1 and G? And if I pick any other G, like if this is my G, then the right is G minus 1 and the left is G. And so that's how my energy groups are defined. And again, we use that backwards indexing because neutrons start fast at 0, and then as they scatter, they end up making their way down to the lowest group. As they have scattering events, they could possibly make it all the way from group 1 down into group capital G. So with this in mind, what we are going to do is we're going to take that energy dependent diffusion equation, and we're going to integrate that equation term by term over that little energy group. So this equation is just the energy dependent diffusion equation, but we're integrating every term with respect to that energy over dE along that energy group. So if we want to move forward, it is helpful to define the group flux. So the flux for a specific group as just being the integral of our scalar, of our energy dependent flux over the group range. So we're saying if we take our energy dependent flux, phi of R and E, and if we integrate that over our energy range, so from E sub little g to E sub little g minus 1, then this is how we will define the flux in some specific group. So this phi of g is basically like the scalar flux just for neutrons of group little g. So it's a scalar flux of just group G neutrons. It represents the path length rate per unit volume per unit time being made by the neutrons that belong into group little g. So if we have this definition, we can go term by term with these, we can go term by term in this equation and understand how this will simplify for what we're trying to derive, which is a multi-group diffusion equation. So if we just break everything up term by term, that's how we could spell out the terms and explain like what they are representing. Previously, everything was an energy dependent reaction rate density. And now we're taking that and we're integrating out the energy. So that means that each of these terms is going to have units that just look like neutrons per unit volume and per unit time. Because originally they had per unit EV units, but we're taking every term and we're integrating over energy, which is adding an extra EV that's knocking out the per unit EV units that we're going to have over here. So once we integrate over energy, now every term just represents a regular reaction rate density for the for each specific group. So each of these, my thing is in the way. Put that up here. So yeah, each of these is either a production or a loss just for the neutrons in group little g. So what we're going to do next is we are going to multiply top and bottom of every term by something that's going to allow us to be clever about the definition of an average, and that's going to make stuff simplify quite a bit. So what we want to do is just think about and remind ourselves that the definition of an average function, like from like calculus, Cal 2, I think this is covered. If you want to talk about the average value of a function as an integral, then you're taking your function times some weight function, and you're integrating that over the whole domain of the function, and then you're dividing by the integral of that weight function. And it depends on the context what that weight function is. If it's like an engineering class, usually those weight functions are some kind of like distribution. Like if it's a probability distribution, that's awesome, because then the weight kind of physically that ends up making sense. So we're going to do something similar. And this is how it's going to look. So this term is equal to itself, right? Like this and what's up here are the same. And don't write what I'm going to write next, but if I wanted to, I could take this term and I could multiply by and divide by 5, right? And that's not changing my expression. And I could even multiply by something more complicated. Like I could multiply by e to the x and e to the x. And that's not changing my expression because I'm multiplying and dividing by the same thing on the top and the bottom. So what if I were to multiply and divide both sides by the integral from e little g to e little g minus 1 of our phi, of our energy dependent flux, dE. I'm going to divide by this integral, and I'm going to multiply by that same integral. That way I'm not actually changing mathematically what my problem is saying. We all agree that that's still true. That's still equal because all I've done is multiply top and bottom by the same thing. And if that's okay, then we can actually look at these two terms. We can group these terms together, and we can look at this on its own. This right here, this integral, what does that represent by definition? Just this integral rate. We're only it's an energy dependent scalar flux is on the inside, and we're integrating it over the group width. So when we integrate an energy dependent flux, what do we get? We get the scalar flux. So this is the scalar flux, but it's only of neutrons that have energies between E little g and E little g minus 1. So it's the flux of neutrons that belong into group little g, which is defined as phi of little g. Right? So that term on the right is just by definition phi of little g that we defined on the previous slide. And notice that this expression right here, doesn't this kind of look like an average? Doesn't that kind of look like a weighted average of the total cross-section weighted to the scalar flux, the energy dependent flux as like my weight function? So if we think about this as an average, then what this big term in the brackets represents is the energy averaged total cross-section for that group. So we can call that sigma t subscript g, and it depends on R. So that sigma t t comma g, that represents the total cross section for neutrons that are in group little g. And then by definition, if I want to get this by itself, then I would divide. If I look at this as my left side and this is my right side, if I want to get the cross section by itself, I'm going to divide both sides by the group flux, and that's how I could end up right here. So by doing this multiplication and being clever about our definition of an average, we took this complicated integral expression for the total interaction rate density, and we simplified it to just an average cross-section times the group flux. And ultimately, we're going to play a similar game with the other terms in our equation. We just have to do a couple extra steps. First of all, with our fission production term, we are going to be clever about how we talk about this probability density function, this chi of E. So essentially what we're going to do is we're going to look at this integral, and we're going to recognize that if chi is a probability density function, and we integrate probability density function over some range, then it tells us like the fraction of neutrons that are being born in that energy range. So if we integrate it over the group energy range, then what I'm saying is that if we integrate from E little g to E little g minus 1 of our fission spectrum dE, what that is going to give us by definition is just the fraction of neutrons that are emitted in group G. So this is the group G fraction. And I might have 100 groups, I might have 1,000 groups. All of my chi G's have to add up to give me 1. Just like in the 2-group model, chi 1 plus chi 2 has to add up to give me 1. So what we do is we normalize this quantity such that if I were to sum up from, let me use a little g, if I sum up from little g equals 1 all the way up to big G, so if I sum up over all of my energy groups, my chi in that group, I better get 1. We just define the group chi to be the energy integral over our energy group. And then we normalize it such that each of those little integrals, if we add all of them up, we would get 1. So if we have that definition, then we can take that definition. We can also be clever about doing that same game with multiplying and dividing by the same thing. And ultimately, what my fission term is going to look like is I'm going to have a chi G over K. And then my fission density is going to simplify to a summation. The integral over all energies is going to simplify to a sum going from h equals 0 to g of nu f sigma f. I want to use an r, nu f sigma f of r for group 1 times, for group H, times phi of H, which is also depends on. So that complicated fission spectrum term is going to simplify to a term that looks like this, where we're basically replacing this first integral with the chi for each group, and we're replacing the second integral with a sum that's my fission, this nu f times sigma f times my phi. That's like my energy dependent fission density. And we're replacing this integral with a summation, and we're just summing over all other groups. And that's what H is. H is just a different index that says we're summing up over every single group, just using a different index from the current group, which is G. And in terms of like what the averaging process looks like, this is how this averaged nu f sigma f for group H is defined. But ultimately, that's all that is, this nu f sigma f for group H. It's just an energy group averaged value of nu f times sigma f. And this is a thing where sometimes you'll see people write nu f with an argument and sigma f with an argument, or they'll just be attached and then they'll write the argument just on one of the terms. That's a common thing because usually nu f and sigma f depend on the same things, and when they're next to each other, it's for the same nuclide. So we're just grouping those together because that's a common practice. So ultimately, that's what our fission term is going to end up looking like for the multi-group model. Again, we're just going to play the same game with the other terms in our equation. So when we take our scattering integral, I guess the first thing that we're doing is replacing the scattering integral. We're replacing the integral over all energies with a summation, and we are then doing clever things with averaging to work out what a nicer form of this scattering integral is going to be. And when all the dust settles, you get a term that looks like a sum from h equals 1 to big G of a scattering cross section to go from group H into group G. And this is a function of R times the phi that caused the initial scattering, which is for group H. And that's also a function of R. Ultimately, this is coming from the same place that first term came from. We're replacing some integrals with sums, and we're multiplying and dividing by the same quantity so that we can take advantage of an average. And here we're group averaging the scattering cross section, the scattering differential cross section that tells you about the cross section to have a scattering event that takes you from group H into group G. So this complicated integral, that's just how the energy averaged differential scattering cross section is defined. So we have two different indexes, H and G, because G is the current group that we're interested in, and H represents any other group. And like for the scattering term and the fission term, it's neutrons of other groups that end up going into the current group. Like neutrons can scatter from group H into our current group G, or fission neutrons from group H can produce neutrons in group G. So that's the reason why we need two different indexes, because some things are not starting in the current group that we're keeping track of. And last but not least, we have that net leakage term. And again, we're taking this complicated definition of a net leakage. We're pulling out this divergence operator because this is an energy integral. And so I can pull this operation out of an energy integral. Then what I'm going to recognize from what's inside of here, or really what's left up top, is that if I multiply top and bottom by the energy average of the gradient of the flux, then this gives me another quantity that looks like a group averaged diffusion coefficient. So this ultimately looks like the divergence of the group averaged diffusion coefficient times the gradient of the flux for that group. Where that dg is the group average diffusion coefficient. It's defined from this integral expression. And phi g, again, is the flux of neutrons that belong to group G. This definition is a little bit different than the previous ones because instead of weighting to just the spectrum, here we're weighting to the gradient of the spectrum. But we're not always going to know what the gradient of the spectrum is. So going to the next line, we make the argument that if we don't know about the gradient of the flux, maybe we know about the flux. And if we have the flux, I could get the gradient from the flux. So those things are kind of like, it's not too much of a stretch to say if I can weight this to its gradient, then maybe I can just weight it to the function itself. And then from there, making clever definitions of an average and redefining the diffusion coefficient in terms of 1/3 times the transport cross-section gives us this way to redefine the group average diffusion coefficient. So that was a lot of math and integrals. And what I was hoping to do is just give you some appreciation and understanding for how did they end up with the terms that they end up with, so that hopefully it's not as mysterious. But ultimately, once we put all of those things together, that's going to give us our group diffusion equation, the multi-group diffusion equation. And did I forget to, is this blank for y'all or do y'all, okay, cool, sounds good. Just making sure. So what it looks like is I have my leakage term, which looks like the divergence of the group diffusion coefficient times the group flux, times the gradient of the group flux. That is what my net leakage term comes to. The total interaction term is that sigma T for group G times the flux in group G. That was the total interaction term. And then those were equal to my scattering term and my fission term. And the scattering term looked like a big sum over H equals 1 to G of my scattering cross section that takes me from the current group H into the group of interest G. This depends on R. And whenever I'm scattering, it's the initial neutron that's scattering. Therefore, it depends on the initial flux of neutrons. That's why when you see this term, it's not a subscript G, it's a subscript H, because it's the group H neutron that is scattering into group G. Therefore, it depends on the group H flux. And then I have a plus another summation of my group H to big G of my group averaged nu F sigma F for that group H. And this is about the flux of neutrons. Oh, and I'm sorry, I forgot there's supposed to be a multiplier on this. I'm gonna just bear with me here. So ultimately here we also have a flux for group H. So that is telling me about the production rate of neutrons per unit volume that are being born from all other groups H, because this is telling me about group H cross sections, group H flux. Those multiply together to tell me these are the neutrons per unit volume, per unit energy produced in group H. I add that up over every single group. That gives me the total number of neutrons per unit volume and per unit time produced in my reactor across all groups. And then I just hit this with a chi g over k. And the chi g says all of these neutrons have been produced in my reactor, but only a fraction have been produced in group G. And then the 1 over k is because we're writing it as an eigenvalue problem. So that complicated integral expression has been greatly simplified into something that looks a lot more similar to just a normal diffusion equation, where you will have this equation for every neutron group in your that you consider. So if you have 5 groups, then you're going to write this equation 5 times, where little g ranges from little g will be 1, and then 2, and then 3, and then 4, and then 5. And every time you write those terms, little g is a constant, but when you write these equations, you're always iterating or looping over h. So I wanted to talk about, oh, yeah, so I wanted to talk about how we can think about and kind of expand those sums to like understand more what we see here. I also wanted to realize that this was a steady state equation, but we could write a time-dependent version of it by just including the rate of change term over here. So this equation up top says rates of losses equals rates of gains, but I could make this say change rate equals gains minus losses. And then over here, I just need my change rate term. And so in the diffusion equation, what did the change rate term look like? Times the partial of the flux with respect to what? Perfect, right? Because it's, yes. And then because we are doing, oh yeah, so it's G, right? Because this is the group G velocity, and then this would be the group G flux. And we could be particular that if this is now time dependent, then our flux is now a function of position and time. So I've also included that argument on phi g in the equation if it's a time dependent problem. Perfect. So that's what the time dependent equation would look like. You just add this time dependent term. So that represents the rate of change of the neutron density for group G neutrons. And this is telling you about the rate of change of the neutron density. And the neutron density changes based on the gains of my density and the losses of my density. And this is supposed to be, let's see, because what I was supposed to do is move everything to one side. So sorry about this. This is a plus. I'm moving the total over, so this becomes a minus. It's a minus. And then when I move the leakage term to the right, that becomes a plus. I promise that I do review my slides and try to correct stuff, but sometimes I don't catch everything. So hopefully that it makes sense why I needed to make that change. But yeah, so what I wanted us to do next is get some better understanding specifically about those sums, because those are the things that look a little bit different from like anything else that we've kind of already seen. So what I wanted us to do is just write out what this multi-group equation looks like just for group G equals 1. So if G is 1, then every time I write the equation, little g is 1, but h can still range from however many groups I have. And right now I'm assuming 3 groups just to make it kind of less writing, but we can still see some useful stuff from this. So if I were to write this term out, how many individual terms am I going to have in the sum if I have 3 groups? Going from 1 to 3, right? So I should have 3 individual terms. And h is the thing that changes when I go. So h starts at 1, and g, this is the equation for g equals 1. So this first term is going to look like sigma s to go from h equals 1 to g equals 1. B of r, of r, and then h is 1. So that's my first term. H is 1, g is 1. And it's a sum So every time I get a new term, it's because I'm changing the index on my sum, which means I'm changing the index on H. So what are the indexes on sigma S going to look like on the next term? Going from what to what? From 2 to 1, right? Because now H was already 1. Now H is 2. But I'm going into group 1, so little g is always going to be 1 here. Times phi. And this is phi of phi 1 or phi 2? Because it's for H, right? So that would be phi 2. Perfect. And then lastly, the last one I need to do is H equals 3. So this is going to be sigma S going from 3 to 1, function of R, times phi 3 as a function of R. Right? That scattering term gives us that scattering sum, if it's 3 groups, gives us 3 terms. This tells us about scattering from group 1 into the current group 1. The next one tells me about scattering from group 2 into group 1. And then the last one tells me about scattering from group 3 into group 1. And I can do something similar with my fission term 2. That is also going to have 3 individual terms. And this chi g over k, g is 1. So I'm always going to have a chi 1 over k out front. And then I'm going to have 3 terms inside of these brackets here. I'm starting with h equals 1, right? So the first term is going to look like a new f, sigma f for group 1, times the phi for group 1. And then I have h equals 2, and then I have h equals 3. So this one's a little easier because it's only one index that we have to keep track of, right? So hopefully we can see the next one is going to look like new f sigma f2 times phi 2. And then the last one is going to look like a new f sigma f3 times a phi. So that's what it looks like if you expand those sums. And don't be scared of them. They're just sums. And the only real thing you have to be scared of is how many energy groups do I give you, because that tells you how many equations you have to write and how many terms will be in each equation. So the way that this equation is written, if I were to group terms together by which terms have a multiple of phi 1 and phi 2 and phi 3, that's what I was doing here. So anything that has a phi, so this has phi 1, this has phi 1, and this also has phi 1. So if I move the sigma s term to the left and factor out the phi 1, that's this guy. Similarly, this is the term that's attached to phi 2, so I move it over and it has a minus sign. And this is the term that's attached to phi 3, so I also move it over. So that I have like loss rates equals 1 over k times my fission production terms. And so notice that this kind of looks like an eigenvalue problem because I have a 1 over k and I have losses and gains. But it also looks like a matrix equation because I have a bunch of constants times a flux, 1, and then a constant times a flux 2, and a constant times a flux 3 on the left. And on the right, I also have this constant times a flux 1, constant times a flux 2, constant times a flux 3. So it almost looks like I could rewrite that equation in this following matrix form, where I have a column of group flux components, and then I have a loss matrix that corresponds to the terms in those terms, and I have a gain matrix, which is P, that corresponds to these terms, each without the sum, without the flux terms. So if we were to take that, this is the equation that we just wrote, and if we were to look at the matrix version of this equation, like if I have a bunch of groups, then I'm going to have, this is my equation for g equals 1, this is for g equals 2, this is for g equals 3, and if I had big G numbers of groups, then this could go down for as many groups as I had, and it's also going to end up going to the right as many groups as I had, because I ended up with 3 terms. That means I have like a phi 1 and a phi 2 and a phi 3, but if I had 4 groups, then I would have 4 terms this way, and I would have 4 terms that way. So the top line is the left side of the equation that we just made. The top line of the Q matrix is the right side of the equation that we just made. And then they are both being multiplied by the group flux column vector. And to make it an eigenvalue equation, we have a 1 over k on the production side. So generally, anytime that you have a multi-group diffusion problem, if you write out all of your equations for each group, you're going to get a matrix. And sometimes matrices are scary, but also sometimes they're cool because they make things way easier to solve if you have to deal with it. So what we already saw is how we can break up this scattering term to say, if this is what my term looks like for group 1, I have scattering from 1 to 1, from 2 to 1, and from 3 to 1. So if I'm scattering from group 1 into group 1, have I changed energy groups? No, right? Because I'm in the same group that I started in. So we give that a name. That's called within group scattering. Right? We're scattering from our current group into our current group. So it's like maybe that's a collision where we don't lose any energy at all, and we just have like a collision where our energy is unchanged. That means we're still in the same group that we started with. If I go from group 2 into group 1, which energy group has higher energy? Group 2 or group 1? Be careful, because if it's 1, right? Because we go backwards, right? Because if we actually, I'll just go back on the slides. The indexing can be tricky, but just remember that we do backwards indexing. So E0, that's like the maximum energy. And then EG, that's like the minimum energy. So E1, yeah, E1 would correspond to like group 1, and that would be the fastest group, and then group 2 would be the slowest group. If there's two groups, group 2 is the slow group, and group 1 is the fast group. So we're going from group 2, which is the slower group, into group 1, which is the faster group. So we've scattered up an energy group. So we would call this term upscattering, right? Because we went from, if I just draw, actually, this might be a nice illustration. If this is group 2, and this is group 1, and this is my energy axis, if I'm going from group 2 into group 1, then I am scattering up into a higher energy group. So 2 to 1 represents upscattering. What about 3 to 1? Is 3 to 1 upscattering or downscattering? It's also upscattering, right? Because I didn't draw the third group, but I could draw my third group here. And then it means I'm starting in group 3 and I'm scattering into group 1, right? So both of these are actually upscattering. And that kind of makes sense that group 1 is the fastest group. So we have within group scattering, because you can scatter from your group into your current group. And we have upscattering, because you can start at a lower group and end up at the higher group. But there's no term that looks like downscattering, because if this is the highest energy group, then there is no higher group that I could downscatter into. So there's no downscattering for the highest group. And similarly, and we'll see something similar when we look at the last group. So this is the equation for group 2. This is this is how this sum would be expanded for little g equals 2. So notice when it's little g equals 2, these we're always scattering into that second group. If I'm scattering from group 1 into group 2, is that down scattering? And I'm talking about now for this second group. If I go from group 1 into group 2, am I up scattering or am I down scattering? Down scattering, perfect. This is representing down scattering. Two to two, that's within group scattering, right? Because we're not changing groups. And then if I go from 3 into 2, is that up or down scattering? up, right? Because I'm going, in this case, it's going from 3 into 2, which is still going to a higher group. So like if you think about these three groups, if this is 1, 2, and 3, if I'm in group 2, then I can scatter down from group 1 into group 2. That was the first term. I can scatter from group 2 into group 2. That's the middle term. And I can also scatter up from group 3 into group 2, right? So that's those three terms. Yes. Yeah. If there's, I think we were basically just ignoring within group scattering on that one. Yeah. So, oh yeah. No, you're good. I think generally it's a funny thing where like when you only have two groups, you basically are just like averaging everything over two. You only have two groups that you're averaging over. So in that sense, like it doesn't make as much sense to care about within group scattering if the groups are very, very large. Because then it's like if the neutrons aren't scattering in or out of the group, we also weren't really considering energy dependence. So it's like even if it was within the group, but its energy changed, we weren't like factoring in the energy dependence. So it's almost like that term didn't appear in the equations because it wasn't really a loss or a gain, if that makes sense. Like the groups are so big that any within group scattering is basically just like the values aren't changing almost, or at least the population. It doesn't constitute a gain or a loss, I think is like the best way to think about it. Whereas if your groups become smaller, and ultimately what we're going to do with this within group scattering is we're going to lump it into another term. So yeah, we'll actually see what we do with the within group scattering in a second. And so notice for the intermediate group, it could have up or down scattering or within group scattering. And then if we write it out, what we have for the highest group, it's group 3 is the highest group. So these are always 3s. And if you're in the highest group, something could scatter down into your highest group, but you could never scatter up. There's no up scattering in the highest group because, or sorry, this is the lowest. I'm getting my numbers mixed up now. So if we draw our picture, I think it's easier to make sure we don't miss anything. So if this is 1, 2, and 3, if I'm in group 3, I can in scatter within group scatter. I could up scatter from 3 into 2, or I could up scatter from 3 into 1. Oh, so I think I need to call these up scattering, right? No, shit, sorry. I'm mixing my things up now. We're we're talking about all of these are balances going into the current group. So if I'm writing the equation for group 3, it's all about what's going into my current group. So if I'm in 1, I could scatter into 3. That's the first term. That's a down scatter. If I'm in group 2, I could scatter into group 3. That's also a down scatter. And if I'm in group 3, I could within scatter. But there's no up scattering into group 3 because there's no lower group than group 3. I had that mixed up at first, but hopefully that is okay. And that does represent down scattering for group 3. So in general, if you had more, question.
Yes, why don't we talk about like out scattering like from 3 to 2 and 3 to 2?
Well, you can only have you can have up or down scattering. It just depends on what group you're in. So if we only have 3 groups, you can't have up scattering because you can't to have up scattering, there has to be a lower group that you could scatter up into the current one. But if 3 is the lowest, like if this is E equals 0 and this boundary right here is E equals like 10 MeV, then there is no lower group than 3. So there's no way for neutrons to upscatter into group 3 because 3 is the lowest that we have. And it was like the opposite with group 1, where there was no down scattering into group 1 because group 1, this is the maximum energy range. This is the maximum energy we consider. So there is no higher group that could downscatter into group 1, just like there's no lower group that could upscatter into group 3 if we have 3 groups. Good question. Thank you. So ultimately, notice, so this is just rewriting if it was general, if we had lots and lots of groups, this is how you could rewrite those terms. You're always going to have one term that's a within group scatter, right? Going from G to G, that's within group. The second term says that you're going from all groups H equals 1 to G minus G. If our current group is G, all of those indexes are lower or higher than the current group. Like if I'm in group G, if G is 5, say, then this is going to go from 1 to 4. So this is going to go through all of the groups that have a higher index than my current group. So it's at a higher index going into my current index. So is that an up scattering or is that a down scattering? Down. Perfect. Yeah, that's a down scatter. And then last but not least, this term represents upscatter. So whenever you see those complicated sums where there's not like a fixed number of groups, but it's just general, don't get scared by the indexing. Just think about my number line, think about what do these numbers look like, and then think about if my numbers are larger or smaller, does that mean if I'm going, which group am I going into, and is it going up on the energy range or is it going down on the energy range? So if you have all of that understanding, then when we look back at that matrix that we had set up before, we can actually notice something interesting about the way that the terms look, that the main diagonal, these terms are along the main diagonal of the matrix. That's the main diagonal. And then everything above that is what we call the upper diagonal. And everything below that is the lower diagonal. So notice, if you are above the main diagonal, everything represents upscattering. If you are below the main diagonal, everything represents downscattering. And then along the main diagonal, these all represent within group scattering. That's where all of our within group scattering components are. So in the main diagonal, we always have a sigma t for the group minus the sigma s going from the group into that same group. And these two terms, we can group those terms together. And if we group the total minus the within group scattering together, we call that the removal cross section. So sigma r for a group is just the sigma total for the group minus the within group scattering cross section. So if you rewrite our equation in terms of these complicated, in terms of 3 sums, up, down, and within group scattering, and then turn the in-group scattering term and the total into a removal cross-section, then this is how you can rewrite the multi-group diffusion equations. And this is what our loss matrix is going to look like with removal terms instead of the t minus the within group. In some situations, you can neglect upscattering. That means all of these terms above the main diagonal are going to be 0. And also sometimes you can say, if we were going to make a decision about the groups being like fast or thermal and what we consider there, if it was a 2-group model, we already know most neutrons are born in which group? Fast, right? If most neutrons are born in the fast group, that means that if it's a 2-group model, we can say that chi1 is basically just 1 and chi2 is basically 0. And that's both of these, the no upscattering and the most neutrons are born fast. Those are simplifying assumptions that are made in the 2-group in the multi-group diffusion equation for 2 groups. Those are simplifying approximations that can get made. So based on what we've covered today, we should be at a good point to be able to make progress on the last homework. In homework 3, it's about half reflector stuff and more diffusion stuff, and then the second half is this multi-group stuff. The main derivation from the multi-group stuff to focus on is these derivations for the two-group model. And this is the question on your homework. So mostly just like in terms of preparing for the exam and derivations to know how to do, the only derivation I would ask you from the multi-group stuff is the question that you have on your homework, where you're doing all this two-group approximations for K effective and for the ratios of like the group flux components. That might sound, if that sounded complicated before, hopefully now after class, when you see that problem, it'll make more sense. And that problem is also in Svetkov's notes. I gave you the page reference. So hopefully that'll be okay to follow after class. As always, if you have questions or need help, let me know. We'll have our help session on Friday. So if you have any questions about the homeworks or exams or anything else, Friday is a great time to get those done. Hope you'll have a good rest of your day and a good weekend. Good luck preparing for the exam. Be aware we do have our exam in class on Tuesday. Yes, it's here. Thank y'all. Have a good day and I'll talk to y'all soon. Hey.
Would it at all be possible for me to take some courses early for some of the weeks that are coming in?
Probably not. I mean, I guess the answer is that it depends, and it depends on if the reason for not being in class is like an excused absence or not.
Not necessarily excused absence. I got a work thing coming up and it's
Gotcha.
gonna be from like all day, starting from 10 to like 10 PM or so.
Gotcha. Okay. I'm sympathetic for that. So if you want to like if class starts at 10, if you could take it before.
Could I get here like an hour early or something?
Yeah, just shoot me an email and we can work it out.
It might have to be like a little bit earlier than an hour because it's
Yeah.
over on Highway 30.
No, that's cool. Like if I need to get here at 8 a.m., I'll get here at 8 a.m.
I really appreciate
Yeah,
that.
for sure.
Seriously, thank you.
Yeah, you're welcome. Have a good day. You too.
They record the house sessions.
Yeah.
It's sometime.
2 to 3:30. Yeah.
Thank you.
You're welcome.
I have a question.
Yeah.
Are you gonna post like the quiz answers?
Oh, I can. Yeah. Was there any? Yeah. Actually, if you want, you can just take a. I will post these. I have the key right now. So if you wanted to take a picture of the key, you could. But yeah, I could post these.
Wait, is that for speed?
Yeah.
Oh, cool.
Yeah, I have an objection, I guess.
Oh yeah.
So for this one,
Mhm.
I'm pretty sure this is right, reactivity.
No, the issue there isn't so much that that is wrong, but the issue is that if you just like, we know that reactivity is a metric that can tell us about the criticality state. And
Okay.
the issue there is that you're writing all of the possible things, but you're not labeling them. So
Oh,
if I
I
see
thought-
that looks to me like it's just writing things down, but not giving the extra. So like what I was looking for
Yeah, this is
was
critical.
was K
Yeah.
equals 1 and rho equals, well, I guess I wasn't actually looking for rho either because
You're looking
part of
for,
that,
buckling.
the
I guess.
bucklings and the lambda, because we hadn't talked about rho yet.
I just remember that from 301, that's why.
Gotcha. Yeah. It was just, I think it was more of a thing where like when I saw them without the label, it was like I didn't know. It's hard to, yeah, that was just the issue, is that they weren't labeled, so I didn't know. Yeah.
Yeah, quiz one key.
I do, but it's downstairs.
I guess.
You're welcome. And if you have any questions about it, feel free to let me know. Shoot me an email or however is helpful for you. Hello.
Hey, two things.
Yeah.
One, it was still working real quick.
Oh, yeah.
Thank you.
Yeah.
Okay, so it's about which one over the last one is the cause where the energy ranges. This is a like zero, I mean, the refill. Is it the reason it can't go up like this? Yeah, scattering, because if this is a zero MEV, there's nothing that it can collide with to gain energy because it's at the lowest or.
Oh, so I guess what we were saying about that, and if it's okay, I'm just gonna show my, go back to that slide. Because, so what you're saying is for the lowest group,
Yes.
which is group 3, we could downscatter into the lowest group,
Yes.
but we couldn't upscatter. So it depends on which group that we're monitoring. I think that's the main thing with this, is that if we're monitoring group 2, then what we were saying is that for group 3, there's only scattering into the group from the higher groups, right? Like I could go from 2 into 3, I could go from 1 into 3, I could go from 3 into 3, but there's no lower group. That's why for group 3, there's no in scatter or up scatter. You can only down scatter into the lowest group. And also, if this is the group that I then this is the group that I could scatter up into from 3 to 1 or from 2 to 1. And I could within group scatter, but there's no higher group that I could down scatter into the group that I'm monitoring this group.
I think that's what you're saying.
Yeah.
Okay, so for group, this was the grouping question. You could go in, you
Yes.
could up scatter, down scatter, and in scatter.
Yeah.
Okay,
Yeah, and then if you're looking at it in that matrix equation, so when you're talking about this middle group, that's the middle equation. So in this middle equation, this is the main diagonal. Everything below the main diagonal means that I'm scattering from a higher group into the current group. So that's like my down scatter, right? That's like scattering from 1 into 2. And then this term right here is on the above the main diagonal. That's the scattering from 3 into 2, which represents upscattering,
nice.
right? So
Okay.
that's everything. All of these terms are going to be upscattering, and all of those are going to be downscattering. And then that within group scattering from 2 into 2 just finds itself along the main diagonal.
Okay. Perfect.
Yeah.
That answers that. The other question was, do you have a copy of quiz 3? Because I wasn't able
Yeah.
to.
Somewhere. Oh, actually, you know what? I probably don't. Because I think what happens is that I was doing all this grading at my house and I just have a big blank of empty blank. But if you want to just take pictures of the key,
The only reason is I want to try it at least
oh,
before.
okay, gotcha. Yeah, that makes sense. If you have a couple minutes, I could go downstairs and I could run a copy for you.
That works.
Cool.
Thank you.
Yeah. Hey, yeah.
So you said for 2 group, it's 95% in fast.
Yeah.
So you can just set the slope to equal to 0.
Yeah, you can set the fraction going into the slow group to be easier.
Is it the same for like 3 groups? Since like the fast group is the first one, so
Yeah.
can you just make 2 and 1?
Um,
I mean, well, it's 2 and 3. Yeah.
It's one of those things where when we set up multiple groups, we don't have to have them have the same energy range. So that's part of it. It like depends on what the range that we're defining. So like usually when we're defining like the thermal and then the fast, it's like this, if we're doing that 2-group model, and this is like 0 to 1 EV. And then fast ranges all the way from 1 to like, 10 MeV or something like that. So this is almost the entire energy range. Therefore, if our fission spectrum is like that, then it's only a very tiny fraction that are getting
Okay.
born in this energy group, and the vast majority of them are being born here. And like, if I break this up into like, maybe I define another intermediate group so that this is like 10 to the 5 EV, and now we're on like a log scale. Well, the more groups that I have, like it allows me to basically just break this distribution up into more pieces, I guess.
Yeah.
But it's going to depend on the ranges of these intervals. And like the ranges of those intervals is really what tells you if you're making an accurate like a multi-group approximation, because you're free to make whatever assumptions you want about the chi1, chi2, chi3, but like, so to me a 2-group model where I say chi1 equals 1 and chi2 is basically 0, that makes actually more sense than that way of breaking it up using fractions makes more sense than almost any other alternative without using the fission spectrum to calculate and say like what percentage you're falling into what groups. Hopefully that didn't like directly answer your question, but hopefully it kind of hopefully it makes
So
sense.
the reason you can't do it for 3 group because intervals aren't like consistent.
Yeah, and
Okay.
if you did do it for a 3rd group, you would just have to maybe be a little careful about like Like if I was gonna do that, actually, what I would do is I would integrate, like if I wanted to set up this energy range and I wanted to set up this energy range and I wanted to say like, what's a good value for chi1 and chi2 and chi3? What I could do is I could take that chi of E and then just integrate it over that energy range. So like, it, that's there's like a semi-analytical expression for this. That's how I got that graph that I showed you. So this is just a function that you can integrate over whatever these bounds are. And then, you know, if this is 0 EV and this is like 1 EV, then that integral is going to give me this fraction. And then if I reevaluate the integral on this interval, that would give me this fraction. And if I reevaluated the integral on this interval, it would give me that fraction.
Oh, that makes sense.
You're welcome. Alrighty, let me just close all this down
Yeah.
and get
Great.
over there.
Also kind of adding on to what he was asking about, if chi2 becomes 0 because it's basically negligible, doesn't that mean it just kind of zeroes out everything that chi2 multiplies by, which makes it significantly
Yeah, so if I actually just, if we're looking at these equations, notice that in my, that the chi appears in my G by G matrix. So like if chi2 and chi3 were 0, then these are all going to be 0, right? Because all of these rows have chi3, all of these rows have chi2. So it would greatly simplify my G by G matrix if I had parts of my spectrum that I said no neutrons were being born in this group, because then it's going to make that all those Q terms being 0.
got it.
Yep. How's your summer going so far?
Oh, could be less stressful.
Yeah. Are you taking other classes?
Yeah, they include tanks.
Ooh, okay.
Things, so.
I see it, yeah.
I like it. First time teaching. So, yeah, I can still as usual.
It's been busy. The planning the lessons just takes me a lot of time because I want to make sure that I'm understanding the material before I present it. And so a lot of what I'm doing is kind of reteaching myself as I'm reviewing and planning my lessons so that like it's understandable, but also so like I feel good about what I'm presenting. Hello. It might not be obvious, but you might not have noticed, but I do get nervous, especially like when I'm starting my presentations. And so for getting into the groove and but also just like knowing that like I have prepared makes it easier because it's like I spent like 20 hours putting this together, so I think I should know it well enough to be able to explain it.
There's some.
Was it quiz 2 or 3 or both? Okay.
It prints off to the second floor, right?
Yeah, it prints out right by Lori's office.